Yeah, so thanks a lot. I would like to thank the organizers for inviting me and giving me the opportunity to speak here. So let me just say, sort of being in Dublin, I don't think a lot of people know that Schrödinger spent a considerable part of his career in Dublin, and so the effects are still visible. So it's a great pleasure to be here as well and sort of keep the Schrödinger and Dublin connection. Okay, so the title of my talk is Enumerative Geometry and Integrability. So the idea is I want to mostly give an overview talk of things that I like. And then in the end, I'm going to talk about my joint work with Reinier Kramer. So it says in progress, but it's simply because I didn't manage to finish it to put it on the archive. So it'll be on the archive on Monday or Tuesday, I think. So it's not really in progress. It's in waiting for feedback from friends. Okay. Good. So let's talk about enumerative geometry first. So what is enumerative geometry? So we want to count geometric objects under certain constraints. So the simplest example is, of course, how many lines pass through two given points. I will not insult your intelligence by giving you the answer to that question. So a slightly less simple could be a question like how many conics pass through 5 given points in the plate. So there maybe you have to think for a second. So typically enumerative invariants depend on some sort of numerical data. So you want to give some constraints, and they often come in the shape where the invariants are denoted like this, or this. So we have integers g and d, and then we have some vectors of integers, lambda, mu, and nu, and these are typically non-negative or positive integers. So, and of course, very suggestive, g is going to be the genus of some curve, let's say, and d is the degree of something. So the experience shows that sort of this single case where you only have one partition, this is typically a very nicely behaved sort of structure, very nicely behaved enumerative invariants. You can prove a lot of amazing results on this. The double case is typically still manageable, so it's much harder, but you can still say something. And then the triple case is essentially impossible. And so I forgot who said that. I think it was Kunkov, that the reason for this is that a matrix only has two sides. So that's the reason why sort of the triple case is essentially not doable. And we will see, so I will say one example of this in a second. So the principal example of enumerative invariants in this setting are so-called Hurwitz numbers. So what are Hurwitz numbers? Well, we sort of fix the data that I just promised we would fix. So we fix a non-negative integer g and a positive integer d, and lambda, mu, and nu are supposed to be partitions of that. And then from this data, we're going to define some number b. So this is just sort of a constraint for the number to be non-zero, and it's 2g minus 2 plus the sum of the length of the partitions minus d. And then we define triple Hurwitz numbers as follows. So this is a count. Maybe I want to do this in red so it's a bit more visible. So it's a count from all genus G Riemann surfaces. Supposed to be genus G. So it's a map, so it's a D to 1 map, that's where the D is coming in, to the Riemann sphere. Maybe I should draw the Riemann sphere a bit larger. Okay, and what I want to do is, I want to fix 3 points on the Riemann sphere. So I'm going to mark them blue, then I'm going to fix B many additional points. Right, so I have B points that are marked in pink. Okay, and what I'm going to do is I'm going to count such maps such that I fix some sort of numerical data based on these points that is induced by lambda, mu, and nu. So let's say I take this point here. So this point, because it's a degree D map, has infinitely many pre-images. So these pre-images could, for example, be here. Could, for example, be here, here, and here. And this is a holomorphic map between Riemann surfaces. So these points, so the map has a local degree at each point. So for example, around this point, locally, the map is going to look like. So depending on the point, so it's locally up to a certain choice of coordinates, this is a monomial map. And we call this NP, we call this the ramification index of that point, so of the map at that point. And then for each point in the target, right, so for this point here, I can arrange the ramification indices of the points in the pre-image. And this is going to be a partition of D. And what I just want is that for these 3 points, so the point at the bottom, this is supposed to have ramification index nu. This is supposed to have ramification index mu, and this is supposed to have ramification profile. So this is called the ramification profile of that point. So it's a tuple of ramification indices. And so I want to fix my 3 special points to have ramification profiles lambda, mu, and nu. And then these extra points, I want them to have ramification profile 2 and then only once. So basically what I'm doing is I'm allowing 3 points to have very complicated local structure in the pre-image. Then I allow some other points to have the simplest non-trivial local structure in the pre-image. And then all of the other points have simple ramification profiles. So for all of the other points, the ramification profile is all ones, and this number b is chosen such a map can even exist. So in general, such a map can only exist if such a b. So if b is chosen this way, this comes from the Riemann. So now the double Hurwitz numbers correspond to setting one of the partitions to be trivial, and the single Hurwitz numbers, where you only have one partition, come from setting 2 of the partitions to be trivial. So one thing I want to note is something amazing happens for double Hurwitz numbers that will not play a role in this talk, but I still want to say it, is that the number of the simply ramified points b does not depend on the degree of the map. So it only depends on the length of the partitions. It doesn't depend on the degree. And sort of this has some sort of implications on the enumerative geometry that are sort of implicit in some of the things that I will say, but we're not going to get into. Okay, so this is the main object that I'm going to talk about. So hopefully this is clear. So I promised on the previous slide that sort of these specializations here have different kinds of complexity. So it turns out that these numbers, this is completely equivalent to the character theory of the symmetric group. So of course this is impossible to understand, because the character theory of the symmetric group is very hard. But double Hurwitz numbers and single Hurwitz numbers, they can be understood. And one of the ways to understand them is to relate them to the intersection theory on moduli spaces. The Hurwitz numbers are very closely related to the intersection theory of moduli spaces. And one of the moduli spaces that shows up is the moduli space of relative stable maps. So what we want to look at is we want to look at maps from C to P1, such that C is a Riemann surface of genus G. And then, so I fix a bunch of points, and I fix exactly length of mu many points P, and length of nu many points Q. And then I want that Pi maps to 0 and has ramification index mu I. So the local degree around Pi is mu I, and Qj maps to infinity, and Qj has ramification index. So this is the map. So like this is the space of all maps I just described earlier, where you have one ramification index mu and one ramification index mu over 0 and infinity. So I can always move these points to be at 0 and infinity because the numbers are topological invariants. But I don't force anything else. So I just force my holomorphic map from a Riemann surface of genus G to P1 to have specified zeros and specified poles. And that's it. So this is the only thing that I force. And now this space can be compactified by allowing the source curve to become nodal, so by allowing nodal singularities. And you have to be a bit careful to keep the automorphism groups finite, but I don't want to get into the details. But this is a very natural space to look at, right? So when you want to study double Hurwitz numbers, just look at all of the maps that have ramification profile 0, so mu and nu. And then hopefully these additional conditions with B we can sort of treat as some intersection product on the moduli space. And this is indeed true. So one of the landmark theorems in this field is the Gromov-Witten-Hurwitz correspondence proved by Okunkov and Pandaripanda in 2006. And basically what they're saying is, okay, so I look at the space where I've specified the ramification profiles mu and nu, and now I also want to sort of get the simple ramification, but this turns out to be some cohomological condition. So I can intersect with some very natural cohomology classes that I'm not going to define. But let me just say, so this kind of forces the location of the point in the target, and this forces the collapse of the local degree. So I wanted to say that earlier, maybe I should say it now. So one way to think of these local degrees is you take a topological covering where every pre-image has, so every point has exactly d many pre-images. So you have d sheets, then at some points you allow these sheets to collide. So this is one way to think about this. And these psi classes, psi I, so they control that. that's yeah. So they're the first Chern class of the ith cotangent bundle. So, so for single Hurwitz numbers, the situation is even better. So what you can do here is you can simply consider the so you can simply look at the moduli space MGN bar. So this we have already seen this week. So this compactification of the moduli space of punctured Riemann surfaces. So up to some sort of up to some conditions. And then another landmark theorem in this field is the so-called ELSV formula, was proved by Eckeder, Lando, Shapiro, and Weinstein. And so what this is saying is, well, I have some other intersection product on the moduli space MGN bar, so I don't have to actually look at the maps. I can just parameterize the curves. And so I can write down some intersection product to actually recover single Hurwitz numbers. And so this is a very deep result. And in fact, sort of most of the intersection theory of MGN bar follows from the ELSV formula. So again, psi I is the ith cotangent bundle. And lambda I, so this is the ith Chern class of the but yeah, so the correct sort of shape of this doesn't really matter for what I'm going to say. But the important thing is sort of you can get some kind of cohomological condition to describe single Hurwitz numbers. This is quite an amazing result for several reasons. One of the reasons is that, well, single Hurwitz numbers, so as I said earlier, Hurwitz numbers are equivalent to the character theory of the symmetric group. And so there's a very simple representation sort of explaining these things. There's a counting problem of like factorizations of permutations in the symmetric group. There's a very straightforward way to say this. And my claim is every undergraduate that has seen this symmetric group can actually calculate these numbers in small examples. Of course, sort of the complexity blows up because the symmetric group grows very, very fast in size. But essentially, this is the idea. So the idea is, so I have these, so like the idea is that I can compute these things here. Sorry, somehow my pen isn't working anymore. So these numbers can be computed in a very simple way, but these numbers a priori are very hard to calculate. But this turns out to be I have to think, a lower triangular matrix, sort of relating single Hurwitz numbers to these intersection products here, and so with non-zeros on the diagonal, so you can in fact invert it, and you can use the simple symmetric group stuff to understand these complicated intersection products. Okay, so the question is, very natural question is, what about double Hurwitz numbers? So can we sort of generalize this to double Hurwitz numbers? And so this was proved, I maybe should have written this, so this was proved in 2001. And then ever since, sort of, people have been asking, does this work for double Hurwitz numbers as well? And so, I mean, sort of the punchline is kind of, but not as nicely. So there's like essentially two answers in the literature. One uses topological recursion in something called the Kyoto class. And the other one I'm going to tell you, so works through the double ramification cycle, but nothing as nice as this. But you can still say something. So, yes, so as I said, it's natural to expect some nice expression of double Hurwitz numbers as an intersection product on MGN bar, and a natural way to sort of construct something like that would be the double ramification cycle. What is the double ramification cycle? So I forgot to do it. I actually wanted to cover this up. So let me actually cover this up so that you're not distracted by the equation for now. Okay, so okay, what is the double ramification cycle in mg length of mu plus length of mu? Okay, so what this is the locus of curves that have a map to P1 with zeros prescribed by mu and poles prescribed by mu. Okay, so this is the locus of these curves. And now again, so I would like to sort of impose some cohomological conditions, so to intersect this with something natural to extract this simple ramification at these additional points. And so it turns out that this doesn't work. So, and there's sort of technical reasons why this doesn't work. So you can define Hurwitz numbers as some sort of branch map, and it doesn't factorize as it should. And that's kind of the reason why this doesn't work. Okay. So, what is the space? So this space, so like one way to phrase this existence of a map from C to P1 with prescribed ramification is to say, well, sort of twisting the structure bundle by the appropriate divisor gives you the trivial. So the structure sheaf by the appropriate divisor gives you the trivial. Okay. So as I said, unfortunately, this doesn't work, but this can be fixed by using logarithmic geometry. So logarithmic geometry to the rescue. So pretty recent work by David Holmes and also by Marcus and Weiss has revealed that sort of the main issue is that the double ramification cycle does not really want to live in MGN bar. So what it wants to live in is in some blow up of MGN bar. So it wants to live in some other space, and so there's like theoretical reasons for why this is true. So this has to do with the fact that you can't resolve the Abel-Jacobi map on MGN bar. You can't extend it to the boundary, but you can extend it on a blow up, and then sort of this naturally gives you a definition of a double ramification cycle that you can then push down. But this blow up is really the right space where this thing should live. And so using this kind of machinery from logarithmic geometry enables the introduction of something which is called the logarithmic double ramification cycle, log DRG of mu. And so using this, Renzo Cavalieri, Hanna Markwich, and Dhruv Ranganathan proved in 22 that double Hurwitz numbers are intersection products of log dr with some classes described by tropical combinatorics. This is an inherently tropical construction, but you can actually recover double Hurwitz numbers as an intersection. This is actually very, very nice. So essentially the construction comes using something which is called the tropical double ramification cycle. This is a purely polyhedral object, and then you can essentially. Okay, so one of the upshots of this kind of approach to double Hurwitz numbers is that the theory provides a pluricanonical generalization of log dr. So what this is doing is, right, so this is allowing partitions not necessarily of the same size. Two partitions mu and nu, and then what I want is that their difference, it's a multiple of this number 2g minus 2 plus length of mu, which was the number of simple branch points. So I want this to be a multiple of this, and I record this multiple, which is k. And then I can, using the same kind of machinery, define a twisted logarithmic double ramification cycle, so which we denote by log dr gk of mu. And so the point is that this becomes isomorphic to, so maybe I should have specified that this is the tensor power. So that this becomes isomorphic to the kth tensor power of the logarithmic canonical. Okay. So this is some sort of technical construction. I don't think this audience particularly cares about this. Maybe, yeah. Do you have a question? No? You just looked like you had a question. Okay, sorry, Daniel. Okay, so but the point is you get this generalization for any positive integer k, and then you can use the same kind of intersection theoretic machinery to extract new enumerative invariants as intersection products with this new cycle. Okay, and these things are called leaky double Hurwitz numbers, and they are denoted like this. Okay. So this is kind of what I wanted to tell you about the enumerative. No, they don't naturally occur as a cover. They naturally occur as a tropical cover. We will see this later on. So the tropical machinery gives you some nice interpretation, but I don't think there's a good geometric interpretation at the moment beyond this is some intersection product. Okay, good. So I think so, but I think the person sitting behind you knows this better than me. Yes. Yeah, exactly. So yes. So the leakiness comes from the tropical picture. So that's the reason why this is called leaky. I will explain this. Yes. Yeah, exactly. Yeah. So, yes, I agree. Yes. yeah, exactly. Yeah. Okay, so I'm just saying the name leaky comes from the tropical picture. So this is sort of a very natural thing to look at, right? So you just define the cycle, you intersect it with something that you already know is interesting, and then you get these new numbers. Okay, so this is what I wanted to tell you about the enumerative invariants, and we will come back to that. But now I want to give you a short crash course in KP hierarchy and 2D total lattice theory. So there's a very rich history connecting enumerative geometry to integrable systems. And so this will be quick and very technical, but please bear with me. Okay, so but it starts with a nice picture at least. So there's a very classical theory of solid and waves described by a single PDE. So this is the so-called KP equation. So KP stands for, I'm going to butcher this, Kadoncev-Petviashvili, I think. Yeah, okay, thank you very much. And it describes shallow water waves, and they look like this, right? And so there's been a lot of work on these things. Sort of the main point for me is that this KP equation naturally sits in an infinite family of PDEs and infinitely many variables. So x, y, and t are the first three. So they're t1, t2, and t3. And then sort of you can naturally construct this, for example, using the Lax pair formalism to get some integrable hierarchy. Okay, so the Kyoto school studied this equation in quite some detail and understood that sort of from an algebra geometric perspective, looking at the solution, so looking at the function u is sort of the wrong thing. What you should look at is the tau function. So what is the tau function? Well, it's a function such that log of tau and then the double derivative with respect to x or with respect to t1, sort of in this other notation, such that this is actually a solution. So, and if u is sufficiently smooth, of course, you can always do this, right? So you integrate by x twice, and then you take an exponential. And this turns out to be the correct thing from the algebra geometric perspective. The big theorem is that these tau functions here, they are parametrized by an algebra geometric object called the Sato-Grassmannian. So, okay, so these are subspaces of Fredholm index 0 of some infinite dimensional vector space with respect to a certain projection. So there's a lot of sort of words, but what I'm saying is actually very explicit. So I want to give you one example. So given a matrix of full rank, right? So you obtain a solution by taking minors. So what you do is you look, for example, look at this matrix. You look at the 1, 2 minor. So then this is the term corresponding to the 1, 2 minor. So you have parameters kappa 1, kappa 2, and kappa 3 corresponding to the columns. And so then you have kappa 1 to the I and kappa 2 to the I times ti appearing as a summand in the exponent. And the coefficient of this exponential is the minor of this matrix. Right? And so I look at the 1, 3 minor, I get A as the coefficient, I have kappa 1 and kappa 3 appearing. And then lastly, for the 2, 3 minor, I get B as the minor, and kappa 2 and kappa 3. This is very explicit construction. This is something you can just do, and it turns out that all solutions come in this. Something very nice. So let me just connect this to the contents of last week, but just in this sentence, and then I will move on. So Kodama and Williams in the 2010s worked quite extensively on these solitary solutions of the KP equation, and for example, proved that the regular solutions, so the smooth ones, they correspond to matrices coming from the totally non-negative Grassmannian. And they did a lot of great things. So they did a classification, tropical geometry, cluster algebra connections, and so on and so forth. We're not going to get into that. What we want to do is, I want to tell you how the bosonic Fock space formalism allows you to generate these tau functions. So give you an explicit parameterization. Okay, so here's what we do. We look at the ring of symmetric functions lambda. So what is this? This is some limit over finitely generated polynomial ring. So I look at the polynomial ring in n variables, and then let the symmetric group Sn act on it. And yes, so and when I let this act on it, it turns out that this becomes a ring generated by the symmetric power sum. The symmetric power sum pi. So this is the sum over xj to the I over all j. And then I take a limit to sort of allow to do this for infinitely many variables. Okay. Yeah, and so the maps are from lambda n to lambda n minus 1 by letting the last variable go to 0. Okay. So there's a Heisenberg algebra action on the ring of symmetric functions. So what this means is I define sort of jk and j minus k to simply be operations. This is basically everything you need to know. And jk acts by multiplying by k and taking the partial derivative with respect to pk. And j minus k acts by multiplying with pk. So this action also has a unit, 1, where just leave everything invariant, and a co-unit called the co-vacuum, which evaluates all the symmetric power sums to 0, so you only leave the constant. You only leave the constant. Okay, so this is the construction that you have. Now what you do is you define a Lie algebra A infinity hat, which is a central extension of GL infinity. And so this is described by very specific generators Eij, which you should think of as sort of the matrix with only one entry in row I and column J. And you also have a central element C, and then so we can very specifically write down what the commutator is. So this comes from some machinery that's more natural. This is the ad hoc definition. This is one way to describe this Lie algebra A infinity hat. So then you can obtain an action of A infinity hat on the ring of symmetric functions. And the way you do this is, well, you write down this generating function here, which I should have said, so z bar, so this is equal to z plus 1/2. So for some reason you work with the half integers here. And so here I, j, l, and k, they're all in z bar. So the columns are and the rows are indexed by half. Okay, so how do you define this action? Well, you define sort of the generating function of the action, and then you have some, I admit, very complicated expression. And then you look at the coefficient of x to the, so you can series expand this, and then the coefficient of x to the L times y to the minus k. This is going to be some expression in terms of these operators j minus j and jj, right? So it's going to be some expression in terms of that, and that is how EKL is going to act. So EKL, right? So this is the coefficient of x to the L times y to the minus k. I look at the coefficient of x to the L times y to the minus k on the right-hand side. It's some expression in these terms, some polynomial expression potentially, and this is how this action, right? So, okay, and this is of course an incarnation of the boson-fermion correspondence for those people who have seen this. Maybe the physicists are more comfortable with this. Okay, so we can formally exponentiate this Lie algebra to a Lie group by taking exponentials. And let me say, so you have to be very careful here when you actually work with this for things to converge. Of course, if you have sort of just any matrix or any element in A infinity hat, this is not going to converge. We were very careful in the paper. I'm not going to be careful in the talk. Okay, so everything I'm going to say is going to converge, and the argument here is basically trust me, bro. Okay, so okay. So now the theorem that Sato and Sato proved in 1983 is that the tau functions of Kp, they are parametrized using this sort of action. So what I do is I take the group elements G in this Lie group I just defined, I let it act on the vacuum, and then I multiply by the exponential generating function of the operators Jk, and then I evaluate all of the pi's to 0, right? So I evaluate all of, so this is going to be some expression in pi's and pk's, and I evaluate all of the pi's to 0, and that's going to be a tau function. Those are all of the tau functions. Right? So this is an amazing theorem. You can actually parameterize the solutions quite explicitly. I find this to be an amazing theorem. I don't know whether people in the audience agree. I think this is sort of, so, I mean, this is some like quite heavy machinery that I'm throwing at you, but you saw on the first slide, the actual computation is actually quite straightforward. But there's some Lie algebra formalism behind this that actually generates all of the solutions, also the formal ones. So the thing I showed you at the beginning, where you have a finite matrix, right? So yeah, you have a finite matrix. This actually gives you sort of some sort of smooth solution or some actual analytic solution. So this gives you all formal solutions as well. So this also generates just the formal power series solution. Okay, so where's the Grassmannian coming in? Well, it's already on the slide. So the observation is, first of all, that the Shor functions, they form another basis of the ring of symmetric functions. This is, I mean, maybe McDonald chapter 1, something you've learned in your studies. If not, this is just true. So the Shor functions, they form a basis. So I have some exponential here. So this is not going to be a finite expression, but this is going to be some infinite expression. And I'm going to do a very strange trick, which is I'm going to pretend that my variables ti are the symmetric power sums rescaled. This is a very strange trick that you do. But the upshot of this is that I can express now the Shor functions, I can express them in terms of pi. So I sort of pretend that the ti are the symmetric power sums, and I base change them to the Shor functions. Okay, so when I do this, right, because the pi's can be expressed in terms of the s lambdas, I get some expansion of my tau function in p now in terms of the Shor functions. Okay, and they're expressed in terms of p with some coefficients r lambda. And then sort of the Grassmannian version of this theorem that I told you is that an expression of this shape is a solution of the KP hierarchy if and only if the r lambda satisfy the Plücker relations. Right, and so you can write the Plücker relations in terms of partitions instead of the indices. So this corresponds to your typical Plücker relation here. So this is exactly the Plücker relation that you know and love, simply reparametrized. Right? And this is the result. Sorry, my handwriting is terrible, which is why I'm giving a slide talk. It's P12 times P34 minus P13 times P24 plus P14 times P23. Yeah, so this is the Plücker relation corresponding to Grassmannian 2,4, right? And sort of there's some reparametrization using partition. I don't want to write it because I always get it wrong. It's something like lambda I is equal to I plus k. Exactly, yes. Exactly, yes. But okay, but this is the theorem. Okay, so now I think we're coming back to, no, not quite, sorry, one more slide. So you can generalize this entire construction to a more general integrable system. I'm not going to do this as well because it's going to be even more involved with complicated expression. But this more complicated integrable system is called the 2D Toda lattice. And so there the tau functions are of this shape. So you have two sets of variables. So you have two sets of times, T1, T2, T3, S1, S2, S3. You base change to the symmetric power sums. And then you have coefficients r lambda mu. And now these r lambda mu have to satisfy something which are called the Hirota bilinear equations. This is, so this is sort of the like analog of the Plücker relation in the Toda set. Okay, so now we're coming back to enumerative geometry. So Okunkov in 2000 wrote a paper which answered the conjecture of Pandaripanda at the time. And what he said was, well, let's look at this operator F2, which is equal to the sum of the L squared ELL. And then we have that for a formal parameter beta, this expression, which is exactly a legal expression in the setting that we had earlier, right? So you see PKK, so this is the TKJK, right? So this is exactly the thing that we had earlier. So this is a TKJK. And then this is because we have the Toda, you have the e to the sum, then you have the sum over the TKJ minus k. So this is somehow coming from the Toda lattice perspective. But the important thing is that in the middle, you have this operator F2, which is a diagonal operator. So it simply has L squared on the diagonal. And when you do this, right, so you can look at the expansion. So you can simply look at the tau function defined by this. You look at the expansion in the double Shor functions. Then the coefficients of this become e to the beta F2 of lambda, where F2 of lambda is a very specific shifted symmetric function. So I can just write down what this is. So this is, of course, secretly some character coming from the Frobenius formula, if this makes sense to you. And these things are the eigenvalues of this operator. And now what I want to do is I want to base change back from the Shor functions to the symmetric power sums. And when I do this, the coefficients of the symmetric power sums become the double Hurwitz numbers. Right? So, in other words, an appropriate generating function of double Hurwitz numbers is a solution of the 2D total lattice. This is sort of, I think, the more exciting way of thinking about it. You look at the generating function of double Hurwitz numbers, you can find some sort of operator such that this becomes a tau function of the 2D total lattice. So, and this kind of sort of sparked a whole new direction of research. One of the things you can ask is, given a general operator W, can we similarly consider the very same construction and then base change, right? So expand the Shor functions, base change to the symmetric power sums. I get some numbers as coefficients. Do these numbers have some natural interpretation, some natural geometric interpretation? So there's a massive literature on something which is called hypergeometric tau functions. So these correspond to the diagonal operators. And there the answer is essentially yes, and the answer is provided by the formalism of weighted Hurwitz numbers. So in other words, so I'm going to define them in a second, but everything is sort of a base change from the completed cycles Hurwitz numbers, so from the stationary sector of relative Gromov invariant. But when W is not a diagonal operator, essentially nothing is known. Like, we don't know anything. And I was very surprised when I started working on this project that there's no literature on this. No one has ever looked at this. But I suppose the reason is that there's never been an enumerative invariant naturally appearing that doesn't fit in this hypergeometric setting. So, but now this is where the leaky Hurwitz numbers come in now, because leaky Hurwitz numbers cannot be hypergeometric. This cannot be. And the reason they cannot be hypergeometric is because mu and nu are not of the same size, right? So when you look at the Shor function expansion on the previous slide, this is a diagonal Shor function expansion, right? So we had this sort of double expansion in S lambda and S mu. So every time when lambda is not equal to mu, the coefficient is 0 from this diagonal construction, and it's because F2 is a diagonal operator. But because mu and nu are not of the same size, this cannot be a hypergeometric. This cannot fit into the hypergeometric, so not into the diagonal setting. But very excitingly last year, Arkadia, Karev, and Levansky proved that this operator W, which is an analog of this operator we had on the previous slide, right? So on the previous slide, we had sum over L squared EL plus KL. So here we shift everything by K somehow. So here we shift by K half, and here we shift by K. So when you do that, what's happening is that this essentially works. So writing almost, so there's some confusion that is currently resolved via email, but sort of, it certainly works in genus 0, and there's some way to sort of twist the definition of leaky Hurwitz numbers to make this work in arbitrary genus. We are very certain. Okay, but I just don't want to lie. So there's you can ignore it, I think. Okay, so now coming from this whole discussion, I just want to mention that sort of there's a generalization of this operator F2. So this is also called FR. So this is just putting L to the R on the diagonal. And if you look at this operator, what this produces is completed cycles leaky Hurwitz numbers. So you look at the same intersection product as earlier, but you look at the R minus first power of the cycle. Changing the intersection product slightly. And this is, in fact, I think, sort of how to think about about the Gromov-Witten-Hurwitz correspondence properly. So the full statement of the Gromov-Witten-Hurwitz correspondence actually is that using this operator, you recover this, and then we know what the eigenvalues of this operator are in terms of representation theory. Okay. So this, of course, immediately motivates the definition of completed cycles leaky Hurwitz numbers, which is the same construction, right? We have the same shifts. We just take the power R. So, but with all of this, the main issue is that this is now an operator which only has one diagonal, so one shifted diagonal with non-zero entries. So this is an operator without eigenvalues. We have no eigenvalues anymore. And the entire construction, so like basically all constructions in the hypergeometric case, rely on the fact that we know the eigenvalues of the diagonal operator, right? So they're just the entries on the diagonal. And this doesn't work here anymore. So this becomes a much harder situation. Okay, so hopefully this crash course kind of works. So hopefully you have some idea of how this integrability is used in enumerative geometry. So let's come to tropical Hurwitz numbers. So this is going to be hopefully more accessible. So one of the things in tropical geometry that you're interested in are correspondence theorems, which is, so in practice what this means, is you have some classical geometric object, you want to express it in terms of some combinatorial object, right? And so Cavalieri, Johnson, and Markvich proved in 2010 that you can express double Hurwitz numbers as a weighted sum of tropical covers. So I don't want to tell you what a tropical cover is, but I want to work out one example, because I think this is one of these things, it's very simple to do in an example, but it's very wordy to say. All right, so let's compute the genus 1 double Hurwitz number for 3, 1, and 4. Okay, so here's what you do. So you write 3 and 1 on the left, and then you generate graphs, so that map to the line as follows. So for example, you could join 3 and 1 to a 4, right? And then you can split it up again. So for example, into 2, 2, and then you can join it again to a 4. And now this is a genus 1 graph, right? Because I have one cycle, and it has 3, 1 on the left, and it has 4 on the right, and therefore this contributes to this number. So it's a genus 1 tropical cover with ramification profile 3, 1 on the left, and ramification profile 4 on the right. So this is exactly how this works. And now this comes with a weight, and the weight of this is the product of the inner edge weights. So I have 3 inner edges, so it's 4 times 2 times 2. But I have to divide by the automorphisms of the map, where I can exchange these 2 edges without changing the map. So I divide by 2, and this is 8. Right? So, okay. I think this is very simple. And now I just do all of the cases. So all of the ways. So in this case, I worked it out before. It's only 4, so I can actually draw all of them. So I can also do this one, and I'm going to spare you the map. The map is always down to the line. So you can of do the same thing, so you get a 4, but you can also split this into 3 and 1 and 4. So of course you could also split it into 0, but then the inner edge weight is going to be 0 and the contribution is going to vanish. So here we get 4 times 3 times 1, so this is 12. Then you can also split the 3 into a 2 and a 1. You can join the 2 1s, and then you can join the 1, you can join the 2 1s, and then this becomes a 2. And then you can join the 2 2s to a 4. And so here the inner edge weight, I believe, is 2 times 2 times 1. So this is equal to 4. And then hopefully the last one is 6, if I did this correctly. I'm sorry, this does not join. So what I get is I split this up again into a 1 and a 2. And then now the 2 joins with the 1. I get a 3. And the 3 and the 1 rejoin to a 4. And indeed here the edge weight is 2 times 3 times 1, which is equal to 6. And I believe 12 plus 8 plus 6 plus 4 should be 30. All right? And this is the Hurwitz number. And this is how you compute this. Right? So this is what tropical geometry tells you. We have this very complicated geometric problem. There's many ways to compute it. I like this one the most. Okay, so what are leaky Hurwitz numbers now? Cavalieri, Markvich, and Ranganathan proved a similar interpretation works for leaky double Hurwitz numbers. We tropicalized it for the completed cycles using the operator. So again, I just want to show you how this number works. So what I do here is, right, so I have 3, 1, and I look again at the genus 1 case with leakiness 1. So k is equal to 1 here. Okay. So what's happening is I can once again join these two. So now I have 3 plus 1 is equal to 4, but because I have leakiness 1, I have to subtract 1. So that is the rule, right? And this is why it's leaky. So this fact on the previous slide that 3 plus 1 is equal to 4, so this is called the balancing condition at each vertex. The edge weights on the left is the same as the sum of the edge, so the sum of the edge weights on the left is the same as the sum of edge weights on the right. And this is just no longer true here. So here, 3 plus 1 is equal to 4, and now I have to subtract 1 to get a 3. So now the 3 can split up into 2 1s, right? 1 plus 1 is equal to 2, differs by 1 from 3, and then 1 plus 1 is equal to 2, and I get a 1 here. Okay, so this is the setting that I have. And then again, sort of the product of the inner edge weights divided by the 1 automorphism that I have, so this becomes 3 over 2. And sort of I have one other case, which is I can split up the 3 into 2 1s, and then I have a 1 and a 1 joining to a 1. and then the 1 and the, sorry, this is also 1, and then the 1 and the 1 again join to a 1, and then this is the other picture that I can have, and here the multiplicity is just equal to 1, and 3 halves plus 1 should be 5 halves, and this is how you get leaky Hurwitz numbers, and this is why it's called leaky. Right? So this is a very nice combinatorial game you can play. No. So you can make them always integers by labeling stuff. So so in the non-leaky case, when you don't have integers, it comes from the automorphisms of the partitions mu and u. And then when you label the preimages, sort of this dies, except in the case h0, maybe I think h0. What about genus 1? No, I think it's just h0dd is 1 over d. And I think everything else is into, I forgot. There's something like that. But yes, so like, okay, so hopefully you understand the tropical picture now. That would at least be my hope. Okay, so something I've sort of begun to care about quite a lot recently is getting closed formulas for these numbers. So this formula on the top of the slide, this is something that Hurwitz proved in 1891. Right? So this is a very old formula, and it's quite amazing. So what it says is that genus 0 single Hurwitz numbers, what are they? Well, they are d to the length of mu minus 3 plus d plus the length of mu minus 2 factorial times this product here. Times the product of mu I to the mu I divided by mu I factorial. This is what single genus 0 non-leaky Hurwitz numbers are. So what about leaky Hurwitz numbers? So these leaky Hurwitz numbers, they're inherently tropical objects. And one thing that always annoyed me is there's quite a few theorems like this in the literature about some version of Hurwitz number where you can get closed formulas. But even though tropical geometry is this nice combinatorial toolbox, we could never actually prove a single closed formula using tropical geometry. Right? So, and then so my claim is we can do that now. So we have a general method how to do this. It's still hard, but it's doable. I should also mention, so there's work by Cavalieri, Markwig, and Schmidt from last year who also proved closed formulas. But my claim is for their paper, you have to be smarter than for ours, because they had to first guess what the formula is, and then you can prove that it sort of satisfies all of the conditions. We can actually generate what the formula is. So you don't need to be as smart. You can just calculate what the expression actually is. Okay. So what's the idea? So we can do it for 1-part and 2-part Hurwitz numbers. So meaning I have exactly 1 entry in my partition for now, or I have 2 entries in my partition. Okay. So for 1-part leaky Hurwitz numbers, I get an expression like this. So this is a recursive procedure. The bi tell me the number of inner vertices in my tropical cover, and that actually uniquely reconstructs the degree on the left-hand side. So this is a well-defined recursion. The exact shape does not matter, but this is sort of how you can compute them. And I should say the initial thing is, so when b is equal to 1, you just get 1 over n. So this is the initial condition. Okay, good. So now you can turn this recursion into some generating function. What you do is you define a generating function. It turns out that this is the correct generating function. And so if these words mean something to you, of course, this is motivated by topological recursion. So this is the right generating function for the 0-1 case in topological recursion. And then what we prove is that this recursion we had on the previous slide, that this translates to a functional equation between this generating function and this variable x. So this is just some non-trivial work that this actually works. So the way we found this is we found in a special case that these numbers are numbers that are already known in the literature, so they're called Fuchs-Catalan numbers. And then sort of from there we were able to extend this. But now we kind of know how to do it in general. But sort of this is the functional equation that you have. And now you can throw something at it, which is called the Lagrange-Bührmann formula. So the Lagrange-Bührmann formula is an amazing result in generating functionology, which basically tells you when you have an implicit equation of this shape, well, almost of this shape. So you have to massage it a bit. That's why it's a theorem and not not a corollary. But if you massage this a little bit, so this gets into the shape of the kind of function, so the kind of equation you can treat for the Lagrange-Bürman formula, and then you can actually just compute the series expansion explicitly. This is a very explicit formula that I don't want to explain, but the point is we get a very nice and compact description. Right, so for A is equal to K over the R, this is a number that appears quite a lot actually. So you get this kind of expression that this is some sort of binomial up to normalization. Good. So what about two-part? So for the two-part numbers, what we do is we introduce a new variable z. And so we use this variable z to basically parameterize this plane curve, right? So this functional equation defines a plane curve. I would like to have some way of actually parameterizing it, and using this variable z, this works. So you can express x purely in terms of z and y purely in terms of z. Again, this is some work, but sort of people from the topological recursion community maybe are not very surprised that this works, because you just parameterize the spectral curve of the topological recursion machine. Okay, so, and now our claim is, well, you package this in a generating function again, so the two-part Hurwitz numbers. You look at the differential with respect to x1, so the total differential with respect to x1 and x2, right? So this just becomes x1 to the L minus 1 times L times x1 and so on. So you just look at this expression, and then it becomes this. So it becomes this difference of these sort of differential kernels. Okay. So how to extract closed formulas from that now? Well, what you can do is you can apply something which is called the Euler operator. So you define Ex to be x1 times dx1 plus x2 times dx2. And then the observation is that when you apply this to W02, right, so which is just generating function without L plus M, well, what this just does, it just multiplies this term by L and plus this term multiplied by M. This is exactly what this Euler operator does. So in total, what this Euler operator is doing is just transforming the degree. So it is just transforming the generating function to be multiplied by the degree. And now you can use this insight that this Euler operator does not really change the generating function and apply it to this log. And this log is interesting because the differential of this log, so the differential d1 and d2 of this log, is exactly the right-hand side here. Okay, but you first apply the Euler operator, and then you can sort of, once again, massage this a bit, and what you obtain is that these leaky Hurwitz numbers, these two-part leaky Hurwitz numbers, they are extracted from this expression. And the way you do this is, you look at this generating function here, you multiply by the differential because we want to base change something, and when you compute residues, you need to remember how the differentials transform as well. And then the observation is, well, these leaky Hurwitz numbers, they're the coefficient of x1 to the L times x2 to the M. So in other words, these things are the residue of this expression times x1 to the L, so times 1 over x1 to the L plus 1 times x2 to the L plus 1, because then this becomes the coefficient of x1 to the minus 1 times x2 to the minus 1. Right? And then this is simply the residue of this expression, x1 is equal to 0 and x2 is equal to 0. Okay, so this is some sort of trick that you can do. And you plug in your expression of x in terms of z. It looks like this. And now this is simply some computation involving rational functions. Right? So now you just have to compute the residue of some rational function. And when you do this, you obtain very nice closed expression. So you get, once again, some expression in terms of binomials involving this a. Then you have a b, which is k plus r minus 1. And sort of, okay, it depends sort of on the parity of L and M with respect to, so on the, well, sort of on the residue of L and M with respect to B. But you get this kind of closed expression. And you could go further with this. And so if you do this a bit more, I'm pretty certain you can just guess what the closed formula in genus 0 is in general. We didn't do this because the paper is already very long. So this is sort of, so it's already 50 pages, and We wanted to actually go in another direction at some point, but sort of this is now a method, I claim, using the recursive combinatorics of tropical geometry to get closed formulas for enumerative invariants. And so I should say all of these results use some sort of recursion formula. And I didn't tell you earlier, this was very bad of me. How does this recursion that we are using here actually appear? Well, how this appears is, well, you have M, then you have M1 and M2, right? So this is sort of your local picture at the tropical curve. Then you just cut here, right? And then this is sort of the combinatorial procedure, and then you have to work a bit to sort of reconstruct how many things you could get back from it. Because, of course, when you cut here, this again becomes a genus 0, one part. So this connected component is a leaky tropical cover, and this connected component is a leaky tropical cover. 5 more minutes, I think. Okay. So then let me. Okay, I prepared much more, but I'm just going to say a few things. So what we then did is we looked at very general operators. So in fact, much more general than this, but then it becomes incomprehensible in a talk. So we looked at a general off-diagonal operator, where the entries on the off-diagonal are sufficiently nice analytic functions in J. Okay. So and then what you do is you define something like this. So this operator h bar replaces the previous formal variable b. So sorry, this formal variable h bar replaces the former variable beta. So there's technical reasons for doing this. But the point is, from this analytic function in 2 variables, we can extract an analytic function in 1 variable. Okay. So when we choose this analytic function to simply be this monomial, we recover the R completed cycles. Hurwitz numbers case, in the leaky and in the non-leaky case, right? Because the K is built into the function. So it's built into the evaluation of the function. So this is some sort of uniform function describing all completed cycles. Hurwitz numbers leaky or non-leaky. Okay, but the important thing is that we have this function W bar. Okay, and from this function W bar, we can now throw the same kind of machinery at it as we did earlier. And then what we obtain is that, well, we can define some sort of numbers from this by extracting, right, so from the tau function. And then we again can define this generating function y of x. Using very similar methods, we can parameterize x of z and y of z in this way, and this describes some plane curve, right? So we get some sort of parameterization of a spectral curve. And so this is a spectral curve for something called Chekhov Eynard Orantin topological recursion. So this would take too long to explain, but the idea of topological recursion is you basically turn your generating function into a differential. You do the same thing for your generating function for the 2-part Hurwitz numbers, and then there's some general formula which looks pretty horrific when you see it for the first time, to produce more multi-differentials. And these multi-differentials, if you're lucky, when you series expand them, encode your higher, so you're like more complicated enumerative invariants as the coefficients in the Taylor expansion. This is something that works for very many enumerative invariants. So in the past, this has been done sort of on a case-by-case analysis. A lot of work doing this for single Hurwitz numbers. So this was the Busham-Reno conjecture. Then sort of many people worked on generalizing this to the completed cycles case. So there has been conceptual work of Alexandrov, Bishkov, Dunin, Barkovsky, Kazarian, and Shadrin that sort of conceptualized this. And what we basically do is we show that for very general choices of W bar, the corresponding numbers you extract satisfy topological. Meaning, I look at the expansion, so I look at these multi-differentials that I get, I look at the expansion, and these numbers then appear as these coefficients. Or basically all nice operators W. So as long as W sort of satisfies some nice analytic condition, this is always true. So sadly enough, this theorem does not include leaky Hurwitz numbers, so we have to do some sort of limit argument. Repeated cycles leaky Hurwitz numbers as well, but that also works then. So yeah. So let me say one thing. So yeah. Oh, everything. So in our setting, everything works in genus 0. So So these are multi differentials on a P1 cross P1 cross P1. So this is like on a power. So W01 is a differential on P1, and then these things are multi differentials on P1 to D. No. So the point is that the differential. So like this G parametrizes the genus of the counting problem. It does not parameterize the genus of the curve the differential form lives on. So all of these differential forms just are rational. So they are all rational differential forms in this setting. So you can sort of do topological recursion in higher genus. This has one application, I believe, that I know of, using sort of some sort of like, I don't know, not invariants are solved by topological recursion in higher genus. I think in genus 1 though, so it's not that bad. So there you have to choose a Torelli marking, and it becomes a bit more involved. So basically, compute like sort of this expression needs to make sense. Like, what does it mean to compute a residue? Sort of. What's the correct integral, basically? What's the correct thing that you integrate? Question then. So this can be done. It's not relevant for us, but this exists in the literature. Yes. Okay. And basically everything is rational. Well, so it's meromorphic. Yes. Well, and then sort of here everything is rational. So then here everything becomes rational in the actual application. But yeah, so we proved topological recursion in a very general setting. And one thing this gives you, that I sort of say this at the very end, is that once you know that an enumerative invariant satisfies topological recursion, you immediately get a connection to cohomological field theory. So in some sense, you recover some sort of intersection theoretic interpretation on MGN bar, but it's very mysterious. So this is not natural. This is just sort of some ad hoc construction you can do. In many cases, it can be made natural. For us, it's not obvious. So this is one of the open questions we list, sort of understand what is the actual sort of cohomological field theory corresponding. But yeah, so yes, yeah. So okay. So basically, the point is, when your spectral curve is, I think, so when omega 0,1 is equal to x squared dx. So, sorry, it's equal to, I think, z squared dxz. Okay, I forgot. But basically, when the spectral curve is the Airy curve, then we know that this computes psi-class intersections. And so all of the spectral curves that we work with only have simple branch points. Meaning when we compute residues, locally it looks like x squared. That means we get some sort of expression in terms of psi-class, because we can sort of locally do this computation and then arrange it sort of in a graph, for example, and you get some expression in terms of psi-class. So many times this corresponds to some natural class. So for example, when you do this for single Hurwitz numbers, you actually recover the ELSV formula. So you actually recover the Hodge integral that you look at. So it would be very nice to have similar interpretation. And sort of this should correspond to something natural, hopefully, but we don't know. And it's basically, it's once again, I think, a question about the logarithmic double ramification. A secret way, but I don't know. Yeah, sorry, I'm already over time, so thanks a lot.